Recording is rolling. So today is Thursday, October 7th, and I'm going to take you guys through as many of the textbook problems as I can today. You guys remember a few days ago, I assigned you these problems. There's the main homework, and then there's the bonus. And the last few days, I've been giving you guys notes on centripetal force, universal gravitation. We put those together to talk about orbits, tell you guys a little bit about Kepler's laws of motion, that whole thing. So yeah, let's do as many problems as we can today. So first one, number 18. We've got, and this is the homework page looks like this. We're looking for a printout. Okay, this is all posted on Google Classroom. So number 18. Tell you guys too, pay real close attention. I actually skipped number 16. Reason I did that is I usually teach these topics a little bit different order. There's some additional stuff I have to tell you guys. I have to tell you guys about angular speed, like how fast you're like spinning or rotating. But today I just want to go through stuff that you would be able to do, which is pretty much everything but that question. So we're going to hold off on number 16. I'll come back to that later. Number 18 says, adventurous archaeologist with this given mass is trying to cross a river by swinging from a vine. The vine is so many meters long, and his speed at the bottom is given as this many meters per second. The archaeologist does not know that the vine has a breaking strength of so many newtons. Can he make it across the river without falling in? That's to say, is the vine going to break? That's the question. Is the vine going to break? Okay. So I'm doing the notes today how I usually do the notes. It's the same premise, the same story, but I've changed all the numbers. Okay. So I have an archaeologist with a mass of 75 kilograms. For context, 75 times 2.2 would give you the number approximately in pounds. So since we're Americans, this guy weighs about 165 pounds, in case you were curious. He's swinging on a vine that's 7 meters long. And they give you another number. They told you the speed at the bottom. Now, that speed at the bottom, so many meters per second. Do you think that in principle, if you knew the length of the vine and also the starting angle, that would be enough information to figure out how fast he's going at the bottom? Think you could figure that out? Right. Hold on to that idea, because that would be one of the things we solve in the future, especially when we get to conservation of energy, which we're getting towards. Okay? But technically, could solve this down. Do you guys remember Galileo stopped dropping stuff off the tower? And you guys were able to solve that the speed of the stuff crashing at the bottom was equal to square root 2gh. Right? Do you guys think that there's a height change between where we started here and at the bottom that you could figure out by knowing this angle if you did enough geometry? Right? I'm just telling you guys stuff that you're going to see in the future in this class, just as a setup. Right? So your textbook is maybe a little bit nice to you, but they're helping you out. They cut through all that, and they said, okay, let's just suppose that you know his speed at the bottom. Okay, something like that. So is that vine going to break? Right. Well, let's just start with, what if he's not swinging? What if the speed at the bottom was 0, sort of as a counterexample? Because there's something that I want you guys to see from this. What if he's just hanging there at rest? He still has this mass. Is that vine going to break in that case? No, it'd be perfectly fine. Because what is this guy's weight equal to? About
750.
Yeah, 750 newtons. And it looks like the tension in the vine can go up to about twice that number, about 1,500 newtons. Okay, actually, he's plenty safe as long as he's just at rest. Right? The vine can hold him pretty well. Okay. But if he's in motion, he's going around a circular path. Do you think that the tension in the vine would have to be more than his weight so that there's a net force upwards? Hey, that net force would be called a centripetal force, wouldn't it? Okay. That's our entry to be able to solve this problem. So I'm going to go sketch this up real fast. 18, vine, swing, mass. I really want to make a free body diagram. Okay, so we start from here, swing like that. Okay. Free body diagram. F, B, D, free body diagram. Okay. So the fact that he's in motion, yeah, sure, he has a weight down. This is equal to mg. Okay. But he also has, here's this, from this point, the center mass point, also has a tension pulling up. Now remember, if he's at rest, that tension just balances with his weight. But if he's in motion, that tension must be more than his weight. Call it T. You could also do F sub T, like a tension force, so that'd be right too, right? Okay. So that's what the free body diagram looks like. Or this. And I'm thinking that the net force on this guy is the difference between the tension up and his weight down. That be true? Again, if he were at rest, then that would just be zero, wouldn't it? The net force, he would be in equilibrium, tension up, weight down. But he's not at rest. There actually is a non-zero net force, which is acting as the centripetal force. Or centripetal force is always provided by like some classic force. In this case, the difference between tension up and weight down. Okay? I'm going to think about these two as sort of like a system of equations. I mean, if net force is this and net force is also this, then couldn't I just put those two together and say the difference between tension up and weight down must be centripetal force, which is mv squared on r, right? Right? You see that? And the question is the vine going to break? So really, we need to figure out what would the tension in the vine be, and then we'll compare that to the maximum allowable tension. See this break now. Okay. You know what? Since you guys are AP, let's solve this in terms of variables, which actually isn't a huge task because it's just one algebra step. We're just going to add the weight over. So the tension in the vine, which we're solving for, is equal to his weight. Remember, if he's not in motion, that's the end of the story. Okay? But if he is in motion, you have to add on the centripetal force piece, mv squared on r. Sort of a backwards way of thinking of it, but you think of it that way. Okay? Now, yeah, if you're solving this for like an AP FRQ or something, you definitely want to start with this step and then leave this step. But good thing this way is that the tension is going to be augmented by the centripetal effect. Okay? Let's plug in some values. So that's his mass is, what did I tell you? 75 kilograms. Okay. So I said a 75 kilogram mass. If you're plugging in your book values, remember book values are a little bit different. It's applied these on Earth. 10 meters per second squared is the gravity field. I got 75 kilograms again over here. Okay. Now here's where the speed is important. Because remember, if he was at rest, this piece would just go to zero. But he's in motion. I said 9 meters per second. So let's do 9 meters per second. For that. Okay. Again, the book gave that to you, but it is the square root 2gh, where h is the height difference between where he started and where he is at the bottom. So that'll come back in the future. And the radius of curvature. Hey, isn't the radius of curvature just the length of the vine? Right? You guys see that's the radius of the circle? So I can just use the length of the vine as the radius of curvature. And my number was 7 meters. There you go. Try this out. So his weight is 750 newtons. But then I'm going to add on this centripetal piece. 75 times 9 squared divided by 7. And all together, that comes out to 1,600 and some newtons. Over 1,600 newtons. You have to go back to the premise, like all the starting numbers I gave you, and you compare. Remember how his weight was 750 newtons, and that was only half the maximum tension in the vine, so that was all okay. The maximum tension in the vine is 1,500 newtons. Is the vine going to break?
Yeah.
Yes, it is, because it exceeds the maximum. I remember I wasn't able to find this video myself, but I remember one of my college instructors actually had pretty much this exact question, but he had a video of a bunch of guys jumping off a bridge with a bungee cord doing this, and the bungee cord would be able to hold their weight perfectly fine, and that was the only consideration they made. But they hadn't considered if they were swinging, and they did all swing. They were all like in a giant bunch, and that thing broke, and they hit the water pretty hard. So that happened. Next one, number 27. We got an air hockey puck. Some mass is tied to string. It's revolving in a circle. At the other end passes through a hole in the table, has some other mass, and the suspended mass is, this one hanging down here, is in equilibrium. Hey, you guys have seen this before. This looks exactly like your starter question from a few days ago. And also, it looks pretty much exactly like your last lab. Right? Doesn't it? Questions. What is the tension in the string? What is the horizontal force acting on the puck? And then what is the speed of the puck? All right. So number 27. Oh, gotta zoom out. Okay, let's get a table going. There's a puck up here. Right. Now, they said air hockey, so remember there's no friction. You don't have to worry about friction. It's going in this circle. What's keeping it in the circle is it's tied to a string, which goes down below. It's tied to this other lab mass here. Okay, like that. Basic setup. Okay. They have to give you some values. So let's say the mass of the puck is 0.20 kilograms, which is one of your medium-sized lab weights. So that's like 200 grams. Okay. Let's call this mass 0.50 kilograms, which I actually have within reaching distance right here. That's 500 grams. That's this one. So this is this, right? Same thing. Like weighs about 5 newtons. Okay. And there's one more thing you got to know. So they also gave you this radial size, this radius curvature, r. R. I call it 0.65 meters, about 65 centimeters. Actually, if you look at those numbers are kind of in the ballpark of your lab numbers, aren't they? Okay. The size and the ratios of those masses. Okay. So I bet that the tangential speed of this air hockey puck up here, I call it V, I bet that's also probably pretty similar to your lab values too. Okay. You guys were getting speeds of like 5 or 10 meters per second, like somewhere there. Okay. So hope this is that similar order of magnitude. Okay. So first question is, what is the tension in this string? They did say that M2 was in equilibrium. So let's do a free body diagram for M2. It's got a weight down. It's got a tension up. And those two, of course, have to be balanced because, well, it's in true static equilibrium. Now, you guys see, obviously, tension is just equal to mg. Okay. But for AP, this is an FRQ question. If you want to be really safe, I would do this. I would say the sum of the forces in the y direction must zero out, because that by itself, just listing that, could possibly be a point, the way AP likes to grade. Okay. Then I would say, okay, therefore, tension minus M2G must zero out. 0 newtons, right? And then add M2G over, so tension must be M2G. I mean, obviously you can see that at a glance anyway, but that's a process. That might be like possibly 1, 2, 3 points right there, just the way AP does stuff. Right, so let me divvy the paper kind of weird. Makes sense in the end. Gonna solve for the tension right here. So tension is M2G, okay, which is 0.50 kilograms and a gravity field of about 10 meters per second squared. Does that look like 5 newtons? So the tension in that string is 5 newtons. That's the answer to question A. Good so far? Question B is, what is the force holding this top puck in a circle? I bet some of you guys already knew the answer. What's the answer to that question? 5 newtons. This is also the answer to question B. This is A and B. Right? Because this string can only have one tension in it. And that tension is providing the centripetal force. This is A and B. Okay? Now, question C says, what is the speed of that top puck? Like the maybe tangential velocity, instantaneous speed. Okay? Let's solve that here. This is question C. So this is going to go through your centripetal force equation. Centripetal force is mv squared on r. And hopefully there's enough information lying around we could solve for that v. I mean, it looks like there probably is. Let's solve in terms of variables, since that's a good practice for AP. Maybe you would multiply this r, divide the m down, and then take the square root. So let's see. So v squared would be centripetal force. You guys know centripetal force is actually the tension, right? I should have said that, but that's all right. Okay. Times r over m. So remember, centripetal force is not a lone force. It's always provided by something. In this case, tension. So that's actually the tension in the string, okay, or the weight of the bottom one. Okay. So if you square root both sides, that'll isolate your V. Okay, so V is the square root of the tension, which is 5 newtons, times the radial size, which is 0.65 meters, all divided by, you know what? I just got mass here. Let's see if you guys are following. I forgot to put a subscript on this mass. Which mass is this? The top one or the bottom one? Yeah, definitely top one. Yeah, that's M1. Okay. So that is 0.2 kilograms. So that giant square root right there.
Wait, so the centrifugal force is equal to the tension?
It is, yeah. So centripetal force is always provided by some force. But with the swinging archaeologist, it was the net force, like the difference between the tension up and the weight down. Right? In this question, but that was like a vertical situation. This one is horizontal. So, yeah, the centripetal force, there's only one force that matters on the top, like because the weight and the normal force cancel out. So it's just the tension is providing that centripetal force. So, say what's the square root of 5 times 0.65 divided by 0.2. Okay, looking at, that's about right. Remember you guys were getting speeds in the lab that were pretty close to this number? 4 point something meters per second. It's about 4.0 meters per second. Looks about right. All right, that's good. Okay, next one. Number 32. A roller coaster vehicle has mass so many kilograms when it is fully loaded with passengers. And then give us this picture. Right? Well, there's more words, but let's look at this picture. I like this picture. You got this roller coaster, zoom in into this valley and over this hill. Right? Hey, when this roller coaster is down here in this valley, sort of hitting the question they're going to ask anyway, do you think you riding the roller coaster would feel very heavy or very light? What do you guys think you'd feel?
Heavy.
Very heavy. You sure would, because there would be an enormous normal force pushing up. That'd be greater than your own weight. Yeah, and that's what you perceived as like a huge force. You'd feel very heavy. Right? What do you think you'd feel at this point right here?
Light.
Very light. Right? Do you think it's even possible that this coaster might be going so fast that it might even like fly off? Right? In that case, what would you feel?
Weightless.
Weightless. And the other correct answer was very frightened. But yeah, definitely weightless, right? So your weight could possibly go down all the way to your apparent weight, I should say, could go all the way down to 0 if you were in like free fall. Right? So very heavy, very light. What are the actual questions? The vehicle has a speed of so many meters per second at point A, which again in the future you could be asked to solve for yourself. It's the square root 2gh, where this height difference would be that h, right? Okay. And what is the force of the track on the vehicle at that point? Okay. That's to say, what's the normal force? There's another question later, but we'll save that for later part. So, okay, number 32. Got roller coaster like this. Okay. At some point, the roller coaster's here. At some point, the roller coaster's here at point A. At some point, well, later on, we'll get to this point B, top of the hill. Okay. We need a mass of this coaster, so I'm going to make it. Oh, whoops! Sorry, I gotta zoom out. Okay. I'm going to make up my own number. I'm going to say 900 kilogram mass. Okay. You need a radius of curvature of this loop right here. That's the reason I got ruler. Draw a straight line. I'm going to call that radius of, say, 12 meters. 12 meters. And they told you the speed of this thing at the bottom. Gave us that. The speed at the bottom, speed at point A is, I'll make up my own number again. I'm going to say 25 meters per second. Okay. And later on, we're going to get to this top loop. So just for later on, I'll give you this other radial size. and make up a number. I'll call this say 20 meters. Okay. There's one other number that could be important that they did not explicitly mention. What's the one other detail that's important that they didn't say? How about what planet you're on? So you guys know in the background there's a gravity field of about 10 meters per second squared. So that's probably going to be important, right? Okay. All right, this is set up. And the first question is, what is the normal force from the track at point A? Okay. Maybe I'm interested in free body diagram. I'll do that in red ink. Free body diagram in red ink. Okay. What are the forces on the coaster at the bottom? It's got a weight, mg, okay. And it's got a normal force from the track, which, see if you guys are following, is the normal force the same as the weight? No, it's more. It's bigger, so normal force. Okay. Is that? Are there any other forces on that roller coaster? Probably not. I mean, maybe friction, but we're going to ignore that. Okay, so we just care about those two forces. Weight down, normal force up. That's it. Just those two forces. Okay. You guys see how there's a net force upward? Because as the coaster is moving to the right, it's also going to be forced upward. Okay. So I might say this. The net force is equal to the normal force up minus the weight down. Okay. And we're solving for normal force. Okay. I also know that the net force is the centripetal force, which is mv squared on r. I'll let point A for, since we're solving the question at point A at the bottom of the valley. I know both of these things to be true. The net force from the free body diagram is the difference between the force up and the force down. Okay. And furthermore, I know that that net force is acting as the centripetal force. Okay. Think we can put those two ideas together and solve for the normal force? You know what? This is looking like it's shaping out a lot like that archaeologist problem, where this net force is acting as the centripetal force. Is that? So, in terms of variables, the normal force would be equal to the weight plus the centripetal effect, if you like to think of it that way, kind of a backwards way of thinking of it. And now we have all the numbers we need, because, well, I gave you all those values. I told you the mass of the cart was 900 kilograms, so 900 kg. We got Earth gravity, 10 meters per second squared, plus, okay, the mass shows up again, 900 kg. Okay. The speed, instantaneous speed. Okay. Hey, if this coaster was going faster, 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 what do you think would happen to the normal force from the track? Do you think it gets more and more and more? Yeah. Makes sense it would, wouldn't it? Like if you're plugging bigger numbers here, I'm plugging in 25 meters per second for my own example. But yeah, if you made that number bigger, the normal force would get bigger too, wouldn't it? All divided by radius of curvature of, I said 12 meters, so look at that. 12 meters. There you go. Let's see what this comes out to. We got 9,000 newtons from the weight, and then add on centripetal effect. That means the overall normal force is going to be over 9,000 newtons. That's, oh, it's a lot more. It's 55,000 some. Maybe call this to 3 6 bigs. Newtons. That's a huge normal force, isn't it?
Is that safe?
What's that?
Is that safe?
That's the next best question. Is that safe? Yeah, because that's a lot of G's. Wouldn't it be a lot of G's? Ooh, let's do a little side quest here. I wonder how many G's that's equal to. You guys remember what the mass of my coaster was? 900 kilograms. Hey, if you know the normal force, yeah, let's do normal force. The normal force, and you know the mass it's acting on. Let's see what that would be. So acceleration is, now this is not the, I guess this would be like your perceived, your perceived number of G's. Okay, what was it? We're going to compare normal force to mass. So what's this number divided by 900 kilogram mass? Okay. Looking at 62 meters per second squared. Okay. No, that's not the net for. Maybe it should be net. Yeah, I think so. I'll do because that'd be like about 6 Gs. Okay, clearly probably not something you would actually build, but maybe I want to do the actual acceleration of this thing. I'm curious to find out. That goes through net force though. So I'm going to take this normal force, subtract off the weight, which was 9,000. Oops. So 55,900 minus 9,000 newtons. So here's the net force divided by the mass of the vehicle. Okay. Here's the actual centripetal acceleration is 52 meters per second squared, which is about 5 Gs. So whether you consider net force or normal force, either way, you're getting about 5 or 6 Gs. Guess that? About 5 or 6 Gs. Yeah, that's probably not something you would actually build.
It says you can survive 100 Newtons, so it won't.
Yeah, right. Yeah, you guys remember that guy in the centrifuge was going up to like 9 Gs? Right? Yeah. There was a follow-up question. What was the follow-up question? It says, what is the maximum speed of the vehicle at point B for gravity to hold it on the track? Oh, yeah, that's right. Because if this vehicle's going too fast, it would just like fly off. Let's solve for that. Let's see how fast we can go. We're going to push this thing. How fast can this thing go before it flies off the track? Well, go back to this free body or this original setup. I'm going to draw on the free body diagram at point B. This vehicle has a weight. In fact, it's the exact same weight that it was before. Isn't it just mg? Right? That, the same thing as that. Same thing. And there might be a normal force on the track. There probably is. But if we're reaching the breaking point where it's just about to fly off the track because it's going so fast, then what do you think that normal force is approaching? 0. So actually, this could be the free body diagram for just that case where maybe it's just about to go into free fall, the wheels are just about to pull off the track, right? Yeah, that would be the limiting case, wouldn't it? So that's what we're going to do. And the question is, what's the speed that would correspond to that? What is V sub B that would correspond to this free body diagram just being, well, only its weight vector would be the only force. Okay. So for that, I'm going to say that its weight is acting as the centripetal force. Yes, right. Centripetal force, the force keeping it in, on that curved loop, right, is only supplied by its weight, right, and nothing else. So the expression for centripetal force, of course, is mv squared on r. We're now looking at point B, so these values are going to change a little bit. We're actually solving for speed in this case. Okay. To keep it on track and its weight, I'm going to call mg. Okay. Do the picture side by side again. So we got this going on, right? Right. Oh, what's going to cancel out? The mass. Yeah. So if you had an empty roller coaster cart versus one that was full of passengers, would the answer to this question, like the speed, be any different? No, because it mass cancels out. Right? We still need to solve for speed. So 2 algebra steps. We're going to cross multiply the r and then take the square root. So the speed at point B is going to be the square root of g times r. Something, yeah. So that's the answer as a general like a general answer. You could solve this for like any roller coaster of any radial loop, any planet for that matter. So let's do it for Earth, 10 meters per second squared. And I gave you guys a radial size of 20 meters for this loop, 20 meters. So let's go 20 meters. All right. What is the square root of 200? That is 14.1 meters per second. All right. So if you had that coaster going over the hill at about 14 meters per second, well, you're kind of at the limit. If you go 15 meters per second, you're going to be flying. You guys get that one? All right. How are we doing on time? Oh, I think we're doing all right. Okay, next one. This is as far as I got. Yeah, okay. This next one is as far as I got last class, so this will be the last one we do today, and then I'll roll you guys your announcements. Number 37. I know I signed a few more, so we'll do the other ones another day, so before next week, or before next Friday. Objects with masses of so many kilograms and so many kilograms are separated by this distance. I'll draw you guys this picture, but I'll make up my own numbers. Okay. Find the net gravitational force exerted by these objects on a third object of some third mass, placed exactly midway between them, like geometrically halfway. Okay. That's the first question. Now, later on, there's actually a separate second question. It says, at what position, other than infinitely far away, would the gravity zero out? So where could you take that third object, that small object, where could you place it in between? Okay. Kind of like, hey, you guys remember Lagrange points from yesterday? Lagrange points? Sort of like the L1 point, thing like that. Now, we're not at that question yet, so let's do the first question first. There's actually 2 questions packed in there. Number 37. Oh, whoops, gotta zoom out. All right, 37. All right, so we got a couple of masses. And I'm going to make up my own masses different from the book. I'll call this guy 100 kilograms. I'll call this guy 200 kilograms. Okay. Let's say they're separated center to center by a distance of, I'll go 6 meters. 6 meters. Okay. And if that's true, then if I put a third object exactly halfway between those, then wouldn't the distance from that third object to each of the other ones individually be 3 meters? Like 3 and 3? Right? So you got 3 meters and 3 meters. Okay. Which are actually the values we're going to use for this calculation. Okay. Well, I need to give this little guy a mass. I'll call it 50 kilograms. So, 50 kilograms. Right. And question is, what is the force to the left? What's the force to the right? What is the net force? Okay. So what is, or is that what they asked? What is the net force? Make sure that's what they asked. Yeah, net force. Okay. So if I do like a free body diagram, I'm thinking that, well, this thing's going to be pulled to the left with some amount, I call it F sub L. And to the right by some amount, maybe F sub R. Hey, can you guys tell me how long I should make the right force in proportion to the left force? It's going to be the same size, bigger, smaller? What's going to be? It's going to be bigger. Exactly how much bigger? Twice as much. You guys see twice as much? Because if you guys know this form, F equals G M M over distance squared. You guys see how the force is proportional to each mass? Okay. And if this mass on the right is twice the mass of this one on the left, you see that this one on the right is going to pull it with twice the force? So like F sub R, like that? You guys see that? Okay. Now, your book numbers, I think, are a little bit different ratio, but that's what it's for mine. Okay. All right, so let's figure this out. I'll do these one by one. So the force to the left is G, well, some version of GMM over R squared. You just got to identify which masses and distances we're talking about. So I know G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Let's see. This mass on the left side is 100 kilograms. The mass in question that is being pulled that way is only 50 kilograms. And what value should I use for the distance? 3 meters. All right, you guys are on. Okay. And also square that, because GM over R squared. All right, so from all this, we're going to get a number. 6.67 times 10 to the negative 11 times 100 times 50 divided by 3 squared. Okay, so is this number going to be extremely large or extremely small? Extremely small, because we're talking about a force between two objects you could fit in a room, like gravitational force. Yep. How many is that? 1, 2, 3, 4, 5, 6, 7. Got 7 zeros. And then 3, 7 newtons. Yeah, because that's a tiny force. Hey, could you turn this into scientific notation? You'd have to multiply by 10 to the power what? There's 7 zeros, that'd be 10 to the 8. Yeah, there you go. So if I take this answer and I say times 10 to the 8, then I can see whatever these other digits would have been. So it's 3.71. And then, yep, to restore it, you'd say times 10 to the negative 8. Exactly what you guys said. At newtons. So you can think of it that way. Okay. Okay. So we could do a similar process for force to the right. Now, you guys actually already told me what the answer is going to be. Oh, yeah. True. Yeah. You guys want to do a little side quest here? Right, so side thought. Mass is density times volume. Or you could say this, density is mass per unit volume. Okay. And the characters for those would be Greek letter rho, looks kind of like a curly P, as mass per volume, like that.
What's the volume equation for a sphere?
Volume for a sphere
It's like 4 over.
is 4/3 pi r cubed. Right? Did I ask you guys yesterday? If you take you guys remember the area of a circle is pi r squared? And if you're in calculus, what's the rate change? What's the rate change of area with respect to r? What's dA dr? It is 2 pi r. Okay. The idea being that if you were to increase the area of the circle, it increases like its circumference multiplied by a tiny sliver at a time. Which circumference is 2 pi r. Okay. Similar idea with volume of the sphere. Do you guys know what the surface area of the sphere is? How many of you guys want to bet it's the rate change of the volume? Isn't that the derivative? Right? It's true. Same idea. Okay. So yeah, thank you for that question. That was a fun thought process. Right. But let's go back to the main one. Okay. So we know this force is this many newtons. You guys already told me that based on my numbers, the force to the right is going to be double that. Isn't that true? Okay. Maybe I could whip that out real fast, but you guys know it's just going to be double that. So force to the right. You guys can play along with your own numbers at the same time. I got 6.67 times 10 to the negative 11 meters squared per kilogram squared times 200 kilograms times 50 kilograms, all divided by 3 meters being squared. But since this is the same setup as before, except one of the masses is double, but everything else is the same, then the answer is just going to be double this. So times 2, I'm looking at 7.41 times 10 to the negative 8 newtons. I mean, that's what it's got to be, right? If you plug all that in the calculator, it's just got to come out to that. Right? Guys good? And then the net force. F net. Oh, well, wouldn't that just be the right force minus the left force? Right? And so it's this minus this. But since you know that these are a 2-to-1 ratio anyway, then do you guys see that's just going to come out to this number? Right? Because, well, 7.4 minus 3.7 is 3.7. Right? Everybody good? All right. Very last question today. The second part of this premise says, at what position, other than infinitely far away, could you place that 50 kilogram object so that the net force is 0? Where's the force 0 out? So back to the drawing board here. I'm just going to draw this bit. Maybe shift. Where should I shift this 50 kilogram mass? To the left or to the right? yeah, to the left, there's an equilibrium point, probably somewhere about here-ish. So let me redraw that. There's 100 kg. There's 200 kg. They're separated by a distance of 6 meters. And somewhere on this dash line, the center to center dash line, you guys notice every time I've been doing distance, I've been doing center to center, center mass to center mass. The other, like if you didn't know physics and you're back in the lab area, you might say, is it the surface to surface? No, it's like center mass to center mass, right? So probably somewhere about here-ish, I'm gonna guess, the gravity cancels out. Right? It's closer to the small one, so being closer might be stronger. The other one's more massive. Okay, so somewhere it's gonna cancel. So I'll throw my 50 kilogram mass right here. How many guys are thinking that the mass of at the equilibrium point probably doesn't matter itself? Like 50 kilograms, I could probably make it anything, and the distance is the same point. You guys think? I bet mass is gonna cancel out anyway. Good idea. Hold them back in your mind. Let's do a free body diagram. I know that this is being pulled to the left with some force. It's also being pulled to the right, a different force. Gravitation. And those two forces better be the same force. Right? I mean, that's where it would equal out. Force to the left, force to the right. Okay. Those better be the same. Actually, I'll start with that premise. I'm going to say force left equals force right. I shouldn't do that. I should start with this. The sum of the forces in the x direction is 0. Therefore, force left minus force right is 0. Okay, then we get to this point. Okay, because AT might say 1 point. That might be like 3 points. Okay. All right. Well, I know the force left is some version of G M over. Well, I don't know what the location is. I might call this distance x. I'm gonna call it distance x. GMM over x squared. Okay. And like the left mass and then the point mass. Okay. And the right force is GMM. Where we're talking about the right mass. Okay. All divided by guys, what is this distance right here in terms of x? 6 minus x. Guess it's going to be 6 minus x? Guess that? From here to here? Must be.
Okay, that makes sense.
Okay. I'll make Yuki's getting in the way. Okay. Guess he's 6 meters minus x. Right? All right. So 6 meters minus x, quantity squared. Okay. That just looks confusing where that's located. Okay, so this whole thing, 6 meters. Okay, so x and 6 minus x. Okay. All right. Hey, what's going to cancel out? Cancel out. Yeah, this 50 kilogram mass cancels out. This little number refers to the 50 kilograms, right? Now the big M's are different. We got 100 versus 200, so. Okay.
Gravity constant?
The gravity constant also goes away. So even if you change that, it still wouldn't change the equilibrium point. And hopefully that kind of makes sense too. Right? We've got like God turns up gravity, the equilibrium point's still the same spot. Right? Okay. So I've got, let's plug in some numbers. 100 kilograms over x squared is equal to 200 kilograms over 6 minus x squared, where 6 is in meters. Sure. Maybe I could divide both sides by 100 kilograms. Take a look a little simpler. You get 1 over x squared is equal to 2 over 6 minus x quantity squared. Is that okay too? Is that right?
Yeah.
Okay, now what I do is I'm going to cross multiply both sides. You guys know cross multiplication? This up here, this up here. I'm going to cross multiply. Okay. It's going to give me 6 minus x, It's x. 6 minus x quantity squared is equal to 2 times x squared. Okay. What I just realized I didn't last class is, last class I solved this the hard way. Okay. You guys see that you could eventually lead this into the quadratic formula? Okay. But I just realized there's an easier way to solve this. You could just square root both sides at this point. Just divvy this paper and show you guys there's 2 ways to solve this. You could square root both sides and get 6 meters minus x is equal to square root of 2 times x, right? Couldn't you do that? Okay. Add x over, square root of 2 is like 1.414. So if you add another x over, it'd be 6 meters is equal to 2.414 times x. Right, true? Okay. What is 6 divided by 1 plus the square root of 2? I'm looking at x is 2.49 meters. All right. Now, does that number make sense? Let's go back and look at the starting point. Right? Remember, there's a 6 meter total distance between the two. You guys said that the equilibrium point should, like the L1 point, think of it that way, should be closer to the small one, which should be within the first 3 meters. Right? So x should be less than 3 meters. And it is. It's got 2.5. Okay. You guys get that? Oh, yeah. You guys want to do VTV news or quadratic formula? Okay, here are lots of quadratic formula, so let's do that. So you guys remember FOIL? F-O-I-L. Okay. So I got 36 meters squared. I'll leave off the units. Okay. Minus 6x minus 6x, 12x, okay, plus x squared is equal to 2x squared. If you want to apply quadratic formula, you got to get everything set to 0. So subtract this over, I'll get x squared plus 12x minus 36 is equal to 0. I know I dropped the units, but that's just to make this look a little cleaner. Okay. X is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay. And if I have a negative number and I subtract even more, isn't that going to make it even more negative? Okay, which wouldn't make any sense. I better pick the plus one. Okay. You guys know what the answer to this is going to be. It better be 2.49, right? Let's see if it is. What is negative 12 plus the square root of 12 squared minus 4 by, oh, I got 2 negatives. Okay, cancel out. So really it's plus 4 by 36. Close that. All divided by 2. Now when I hit enter, the answer better be 2.49. X is, oh, it's 2.49. 2.49 meters.
Is that?
Any questions today?
When answering that, we put to the left of the mass that we put X on, right?
Say again?
When like writing out the answer to that, we have to show what X means though. We'd say like that many meters left of a certain mass.
Yeah, as long as you said what that was. Yeah. Okay. All right. Yeah, so guess we have a little spare time tomorrow, so if there's anything important in the announcements, then you can catch that then.